I think we can get started.
Hey, nobody got up. Okay, so looks like you guys are serious. Well, thanks for joining us on this last day of Ignite. Everybody have a good time at the party? Yes? Okay, great. Good for you. I skipped that. I had 2 escalations. So anyway, let's move this slide. Oh,
so
sorry.
I guess let's just introduce ourselves. Yep. So thank you for joining us for this session. The topic for today's session is how to get peak performance from your Azure SQL Data Warehouse column store. So we are going to specifically focus on the column store aspect of it. My name is Shivani Gupta. I'm a program manager in the SQL Data Warehouse group. And
I am Joe, as you might have guessed. We both work in the SQL Data Warehouse program management team. I focus primarily on the storage engine and transactions. And Shivani is the PM owner for column store and performance. Yes,
column store is equal to performance in many ways. So let me begin by asking you a few quick questions. How many of you have used Azure SQL Data Warehouse in one form or another? Pretty good, not bad. How many of you are familiar with column store technologies, either from SQL Server? Wow, we have a good set of audience here then. How many of you heard about the optimized for compute offering that we announced this week? Couple, okay, not bad. All right, so looks like we have an audience that is familiar with the basics, so we have a good foundation to start with. So today, myself and Joe are going to be switching back and forth. Basically, our session is divided into 4 parts. We're going to begin by giving you a deep dive into the internals of our SQL Data Warehouse column store. And this is very essential for you to understand the later parts where we give you more prescriptive guidance on what to do. So once you understand how things work, it'll be much more helpful to absorb the guidance. So we're going to establish terminology, explain how some fundamental operations like loads, DML, scans work, how distributions and partitions impact your column store. Next, I'm going to hand to Joe for describing what a healthy column store looks like, how you can monitor for health, as well as what are some of the pressures that you can run into that make a column store unhealthy. Then I will take over again and go through some patterns and guidance that you can implement in your ELT and ETL jobs to set up your column store for success. Because ultimately, the mileage you get from your SQL Data Warehouse depends on how you have set up your column store. So your experience is, to a large extent, determined by what we're going to tell you today. So Joe will get into things like how you maximize row group quality. I will get into how you maximize your row group quality, how you should use partitioning, and we have something called secondary B-tree indexes on column store, how you can use that to handle your needle in a haystack queries better. Then I'll hand over to Joe, who will walk through some of the loading tools, which ones are good, which ones are not so good for loading data into your column store quickly and optimally, and then we'll wrap up. So not everyone had used SQL Data Warehouse previously from the show of hands, so I'll just quickly set the context. We're not going to go deep into the architecture of SQL Data Warehouse, but I do want to orient you so that you understand where the column store comes into play. The SQL Data Warehouse is a fully managed data warehouse service as a service in the Azure cloud. It is an MPP architecture. MPP stands for Massively Parallel Processing. So it is scale-out technology, basically. So what you see in this picture is there is a control node, which is like the coordinator, and there are 4 compute nodes. So whenever a query or a load comes in, the control node sends the individual pieces of work to the compute nodes. So each of the compute nodes has a subset of the data. So your data gets split across these compute nodes based on whatever distribution strategy you chose. So each of the compute nodes does its part of the work and then either returns the results for a query or the status for a load to the control node, which then returns back to the user. So this is basically how SQL Data Warehouse works, just like any other MPP system. What is unique about us versus some of the other cloud data warehouses is that we separate the storage from the compute. So as you can see in this picture, our persistent storage is in Azure Blob Storage. It is not local in the VMs. We do have a new offering which does a lot of caching, and that's the optimized for compute offering which we announced this week, which does some caching in the compute nodes, but the master copy of the data is in Azure Blob Storage. So this sets us up for providing you rapid elasticity because we can quickly change the mapping of storage to new compute nodes that you may add, or even if you shrink, we can reallocate this mapping rapidly without physically moving data around. Within each compute node, actually even inside the control node, we run a SQL Server that many of you are familiar with and love. So we get the performance benefits and execution benefits of SQL Server under the hood in each node. And this is where column store comes in play, because the column store we use is essentially the SQL Server column store. But there are key differences which we will emphasize. So why use a column store, right? I mean, traditionally data was stored as rows in OLTP systems, and it works great for random access to a few handful of rows that you want to read or write. But with analytics, the story changes. Most analytic queries want to access very large amounts of data, scan it, and aggregate it. So in the last decade, column store formats have become very popular in data warehouse / analytics engines. And what they do is transpose your raw data into a column format where values from a column are stored together. And this works great for compression because data from the same domain usually compresses much better. So depending on the data type, we have seen compression from 3x to 10x. Further, if your data size reduces, you can store a lot more of it in memory. And our SQL Server engine and hence SQL DW engine can work on compressed data directly. So you get big performance boost there as well. And another benefit of column store format is that you can, data warehouse tables tend to be wide tables, especially these days. People are denormalizing their data more and more, and they do tend to have a lot of string columns. So, but the queries usually access only, a few columns from the hundreds of columns that you may have in the table. So in the row store, you would have had to read all the values of the columns. But in a column store, the engine basically eliminates all the columns that are not referenced in the query and only reads from this the reference column, so reducing the I/O greatly. Column store formats are also much more amenable to batch mode execution. Some of you might have heard of it or not, but SQL Server does a great job of batch mode execution, also known as vector processing in the industry. This again gives us many factors of performance improvement, and SQL Data Warehouse is able to give you these benefits of batch mode execution on column store. So, always store your large tables in column store. That's how you get performance from your data warehouse. So let's begin by establishing some terminology. A row group is basically a set of rows that are handled together by the column store. The maximum a row group can grow to is 1 million rows. It's actually 1,048,576, which is basically 2 to the power of 20. So that's the precise number. The maximum is the ideal number. But we don't always get that, and we'll get into details of all that subsequently. A column segment is the values from a single column in your row group. So in the picture that you see, the big square box represents a row group, and each of those bars represent a segment. So this table, you can infer, has 5 columns because there are 5 bars, each bar being a column segment. Further, notice that each bar is of a different size. So this is showing the size of the columns on disk. So what we do is we encode and compress each column differently depending on its data type. So, and depending on the number of distinct values you have in a column, as well as the data type, each column can compress to a different extent, so its size will vary on disk. We also have something called dictionaries, which you will come across. A dictionary is an auxiliary structure which is maintained outside of the row group, and it's an encoding that we use primarily for string columns. So the dictionary stores the actual character strings, and inside the row group segment, we store the hash value from the dictionary. So if you look at this row group that I have here, there are two columns with dictionaries, the gray bar and the blue bar. Those are your dictionary encoded columns. Another thing you might come across is there is something called a primary dictionary and a secondary dictionary. A primary dictionary exists for every column that is dictionary encoded. It's basically the global dictionary. It gets shared across all your segments. Sometimes if a segment cannot fit its new strings inside a primary dictionary, it will need to start a secondary dictionary, because the primary dictionary as well as the secondary dictionary can grow to a max of 16 megabytes. So some segments will have a secondary dictionary. So in this example, if you notice, the gray column has a secondary dictionary and a primary dictionary, whereas the blue column only has a primary dictionary. Another key piece of information that we maintain for our column store is metadata about minimum and maximum values in that column. So this is super helpful for us to eliminate segments which fall outside the bounds of our predicate. So let's say this is a line item table, and a segment, one of the segments has data between order keys 1 and 100, but you send it a query with a filter which wants order keys greater than 500. So the engine is smart enough, it can look up this metadata and say, hey, I don't need to read this segment at all from disk because its values are outside the bounds of my filter. So think of it as a built-in index that comes with your column store. Now let's look at what happens when you load data into your column store. So depending on your batch size, which is essentially the set of rows that you're loading together, if your batch size is greater than 100,000 rows, the engine will directly send those rows to compressed row groups. So what you see on the left side, the vertical bars, each of those represent compressed row groups. Each set of tiles represent compressed row groups. However, if you send less than 100,000 rows, the engine determines that this is not worth compressing. It's too few to get good compression. So I'm going to temporarily store these rows in something called a delta row group. A delta row group is a row-oriented structure, which is essentially organized as a B tree, and it holds the rows until there are enough rows, which is 1 million rows, to get the compression going. We have a background process called tuple mover. So whenever a delta store reaches the 1 million mark, it compresses those rows and sends them to compressed row groups. But in the meantime, your queries will have to scan the delta row, which is a delta row group, which is not going to be as fast as reading the compressed row groups. So you certainly want to bias towards having data in compressed row groups versus delta row groups. So next, let's look at how DMLs, specifically deletes and updates, work. If the row, so let's say a delete comes in, and what I have on the right is the delta store, on the left are the compressed row groups. So if the row is found in the delta store, it will be just removed from the delta store. Delta stores are mutable. Compressed row groups are immutable. You cannot change them. So if it turns out that the data is in the compressed row group, you cannot modify it in place. Instead, we maintain a structure called a delete bitmap, and where we turn on the bit for the row that we find is deleted. Okay? So that is how deletes take place. For updates, what we do is it translates into an insert. Basically, a new row is inserted into the delta store, and the old row is deleted, either from the delta store or the compressed row group. All right? So overall, expensive operation. Now, let's see what happens when a query comes in and needs to scan your column store, right? So some of the data is in the compressed row groups, and ideally that should be 99.99% of your data, if not 100% in the ideal case. There might be some bits turned on in a delete bitmap, and you may have one or more delta stores. So how can you end up with more than one delta store? This is if you are running on machines which have multiple cores per database, which is going to be the case in your SQL Data Warehouse, especially at larger SLOs like DWU 6000. Each node will have multiple cores per distribution and is going to try to do intra-node parallelism, and each thread will create its own delta store. So you could end up with, multiple of these. So when a query comes in, it obviously scans the compressed row groups, and bear in mind it will use the segment metadata to eliminate the compressed row groups that fall out of the bounds of your predicate. So it gets the data from compressed row groups, checks the delete bitmap to make sure that those rows, none of those rows have been deleted, and then does a union with the data in the delta row groups. So if all your data was in compressed row groups, your query would run much faster versus having to accommodate for all the other structures. So what we looked at so far was basically how a single column store looks like. Now let's see how this translates to SQL Data Warehouse. So the current offering of SQL Data Warehouse that we have out there always has 60 distributions. Think of each distribution as a database, as a single database. So each distribution has its own column store, okay? So what you see here, each of these tiles, there are 60 tiles, 10 in each row, and 6 rows. So each of these tiles represents one of those distributions, and each has its column store. So the 2 row groups that you see in each tile belong to a column store for that distribution, all right? So this is what it looks like in SQL DW. Now let's add partitioning to the mix. So what happens is, let's say you have defined n-way partitioning. So what this is going to do is chunk up each distribution n ways. So the total number of column stores that you're going to end up with is 60 times n. So this is a little bit different from the SQL Server, in case you're familiar with SQL Server. In SQL Server, partitioning will increase the number of column stores by n. But you have to bear in mind that in SQL Data Warehouse, it will multiply your column stores by 60 times n. So, the impact is much more. You're chunking up your data a lot more. So we'll get into it, get into how you should be judicious about defining partitioning. So if you have an example where, your fact table is partitioned 2 ways, essentially this is what it's going to do to your column store structure. So the 2 row groups in each distribution are now part of separate column stores, assuming the data was uniformly distributed, giving you a total of 120 column stores, all right? We do have a bunch of useful DMVs for you to peek into all of what I have described so far. What's going on with your row groups, what state your row groups are in, and open, closed, compressed. Open essentially means it's a delta row group. Closed means the row group has reached 1 million rows and is ready for tuple mover to start compressing it. And compressed means the obvious, that it is a compressed row group on disk. This will also tell you total rows, number of deleted rows, so a bunch of useful information, and I will demo this shortly. Another DMV that is worth being familiar with is column store segments. There is 1 row per segment in this DMV, and this will tell you things like what was the encoding used for this segment. So for example, dictionary encoding is 3 and 4. So if you see a value of 3 or 4, it means it was dictionary encoded. And if it was dictionary encoded, it will have the ID of the dictionary. It will also give you the min and max state metadata for that column store segment. We also have a DMV for the dictionaries, and the most useful piece of information in this DMV is your dictionary size. This gives you the dictionary size on disk. I'm going to quickly run through a demo to show you some of these DMVs. So what you see on my screen is a view that I have created using the DMV that I just talked about. So this PDW column store row groups is the first DMV that I showed you. And in SQL Data Warehouse, usually you have to join the DMVs with a few other tables, because when you start from a user table name, you have to do a bunch of joins to collect information from all the distributions. We do have this view documented, so you can just pick it up from our online docs and create it for yourself. So first thing I'm going to do is, I have a flights database which has a huge fact table called flights. And this contains information about arrivals and departures of flight information. It has about a total of 137 million rows. And if you divide that by 60, you end up with about 2.2 million rows per distribution. This table, the flights, is 30-way partitioned, which means each partition per distribution should end up with about 76,000 rows. So I'm going to run a query on that view that I just showed, which underneath uses the DMV for row groups, and see what happens. Okay? So remember I told you that each column store is going to end up with 76,000 rows. So what you see here is that for distribution 1, the second partition has 2 open row groups and 0 compressed row groups. So nothing went to compressed row groups because there were too few rows. Everything was added to your Delta stores. And each Delta store has about 38,000 rows. Why it ended up with 2 Delta stores versus 1 is because there was intranode parallelism going on. There were 2 threads doing the load, and I ended up with 2 open Delta stores. So next I'm going to show you a non-partitioned version of the same table. So I removed the partitioning. So flights NP has no partitioning. Now each distribution has only 1 column store, which should have about 2.2 million rows, right? So now we are giving it enough rows. So let's see what this DMV shows for the row groups in flights NP. So notice how there are no open row groups any longer. Everything is compressed. There are 9 compressed row groups per distribution, and each one has about 254,000 rows. So enough number of rows to get compressed row groups, but it still makes you wonder why it created 9 row groups with 254,000 rows versus creating 2 row groups with 1 million rows each, right? So what is going on? And that is exactly what we're going to get into as we start talking about column store health, and you will see how you ended up here. So next I'm going to quickly show you a query on the segments DMV, which shows you the encoding and the min-max metadata and things like that, because this may come in handy too. So what you see here is for each segment, there is a row. And it is showing you the encoding type as well as the min and max metadata. So what you will see in this example is that the min and max metadata for pretty much all the rows is the same. So the local bounds for each segment are pretty much the global bounds. You're not going to get much segment elimination because there is a lack of tight bounds. And further down, we will give you some guidance how you can load data so as to get more locality within segments and hence get better segment elimination. So at this point, I'm going to hand over to Joe to talk about how to check for your column store health and what it means to be healthy.
Thanks. So before I switch over the slides, just keep one of these result sets in mind. The previous query that Shivani just ran, where we were supposed to have everything in column store, but then why do we end up with so many of these? And also, why do we have so few rows? We're expecting 2 million. So keep that in mind, because there are a number of things that affect how densely you can pack each of these row groups. And we talked about partitioning being one of the factors that affect it. We're going to look into some of the others that may potentially cause you grief. So how do we know a column store is healthy? Size of the compressed row groups, or row group quality, as we sometimes call it, really, the target is we want to go to 1 million. And if you're wondering, how do we land at 1 million? Well, we grab a few dice, we throw them on the ground, and we just arrange number, and that's how we land 1 million. Kinda. Well, we actually did a bunch of tests when we were designing column store back in 2012, and essentially we tested it across a wide range of rows and looked at the perf gains that you get. And right around the 1 million mark, somehow magically, that's when things started to taper off. So as you added more rows to it, you really weren't getting much incremental perf gains, and that's where we kind of cut it off, okay, when we pick 1 million. And it's not exactly 1 million with all zeros, it's 1024 by 1024, because that's an engineer that came up with a number, not a marketing person. If it was marketing, you'll see nice 1 and zeros, but engineering will say 1024 by 1024. So that's how we landed at 1 million. It is based on numbers that we measure on performance and what gains we're going to get. Because as we'll talk about in the next few slides, there is impact to how many rows you put in there and the types of columns that you have in these rows. So 1 million seems like a good balance. The minimum that we really want to go to is about 100,000. We call that acceptable. We don't like it, but that kind of works okay. We get some reasonable compression. That means we're going to reduce the number of IOs we're going to pull through. So those of you who are familiar with SQL Server, you know we store data in pages, but in column store, each page contains data from the same column, or a segment, if you will. And reducing the number of IOs, one of the ways you accomplish that is to pack each of these segments as densely as possible. So if you have 1 million and you have low cardinality, you can pack it really tightly. The fewer rows you have, the harder it is for us to get really good packing out of this. The other thing that determines performance for scans is the number of rows in your Delta store. So just to make sure everybody got what Shivani said earlier, and this is important because all of the rows that do not make into compressed row groups are essentially your regular row stores. So this is just like what you currently have in SQL Server today when you don't enable cluster column store indexes. So every IO operation that retrieves data from the Delta stores brings back the entire row. So imagine if you have, well, actually, let's go find out. How many of you have SQL DW tables that have more than 100 columns in a table? Just one?
There you go.
2? Oh, okay, a few more. How many with more than 200? 300? Oh, good. We got a few honest people here. So we deal with that a lot, right? So imagine if you have to go out there and you only need 3 columns, but when your data is in Delta Store, you need to pull all 300 columns back, but you only need 3 or 4 columns. So it becomes grossly inefficient, as you might imagine. So if you see a lot of Delta stores, so non-compressed row groups, that's one of the signs that you're going to suffer in perf. So, and this is one of the things, it scans row by row, it pulls it out, you pull everything back, not the specific columns that you need, and one of the things that influences the number of Delta stores that you have is the higher DOP setting that you have, or higher DOP decisions that we make, or will influence the chances of you having a large number of Delta stores. And we'll walk through that in a little bit in the next couple of slides. Then the other thing is deletes. So remember, column stores are immutable. Once we pack it up, it becomes very expensive to unpack it, find that one chunk that you don't want, delete it, and repack that. So we're not going to do that. That makes no sense. So what happens is we build the delete bitmap, as Shivani mentioned, and every time you bring result sets back, we use that bitmap to filter against those result sets before we send it back to you. So the bigger you delete bitmaps, the more inserts or updates or deletes that you do, the bigger performance impact you're going to take. So remember, there's no direct delete going against cluster column store, or sorry, no direct update. Essentially, we do a delete and we build the delete bitmap, and then we do an insert against Delta row stores, and now you end up having to go retrieve data from that Delta row again, Delta store again. So a number of things here in the background that will affect your perf. A lot of things that you don't even think about when you're doing an SMP, because it really doesn't matter much in SMP, given that you've got this one thing here, and you're all hitting pretty much the same sets of columns or hitting the same set of tables. If you don't partition, even if you do partition, it goes to however many partitions you have defined, as opposed to having a 60x multiplier on top of that. So the stuff that will affect your row group quality, we talked about the load batch size, making sure that you have enough rows. So this is actually implies that if you don't have very large tables, you're probably not going to benefit from implementing column store on top of that. If you have tables and your data marts that you run, and you've got, hey, I've got 20 million rows in my little data mart, I'm going to take advantage of SQL Data Warehouse massively parallel processing. You're probably better off running that on your laptop if you have 20 million rows in that fact table of yours. If you have 200 billion rows, that's a really good candidate. Because the overhead of the MPP, the overhead of building the distributed query plan and going out figuring out where these things are, pushing it out to the compute nodes, that's going to exceed whatever gains you'll get out of the parallel processing. So if you don't have very large amounts of data that you want to push through, you're going to have a hard time building quality row groups. Partitioning, as mentioned earlier, be very, very careful. We fully support partitioning. In fact, we make it a lot easier to implement partitioning. How many of you use partitioning in SQL Server? You love creating partition functions and partition schemes and all that, right? That's so much fun to go write scripts to go create. No? Really? Well, how many of you have used it in SQL DW? Just 1 or 2 persons. So much easier, isn't it? So we make it a lot easier, but that doesn't mean you should go out there and start using that. Be very selective. We talked about this earlier. Every time you partition a table, if you traditionally partition by day and you move it in from SQL Server and you move it into SQL DW, your 365 is now multiplied by 60. That's how many shards you have in your partition table. It's no longer 365 shards or partitions. You now multiply that by 60. So think about the quality of your row groups when you do that. And one of the questions I get every so often is, we have customers that migrate from Oracle to SQL DW, and they come from Oracle RAC. How many of you think RAC is MPP? Nobody? Oh, good. You guys are a lot smarter than some of the other folks that we've talked to. RAC is SMP. It may have multiple nodes, but it works against a single instance, a single copy of a database. That's not MPP. If you move it over thinking, the same design will just work, well, you will be in for a surprise. Now, memory pressure and dictionary pressure, these are somewhat related. Memory, there's general memory pressure. We need memory to be able to collect stuff and compress it. Dictionary, as described earlier, we leverage the dictionary to build the compression table so we know how these things are compressed and what schemes are being used. And all of these things require memory. And if you don't have enough, what happens is you get trimmed. And that means you will have row groups that have fewer rows than is ideal. 1 million is ideal. We can go as low as 100,000 and still be okay. But sometimes you find that you have tens of thousands or even few thousand rows in a row group. That's going to be really bad for performance, and it's also bad for storage. So the range of compression that we've seen in customer workloads go as low as 3x compression, which is extremely low. These typically mean they have high cardinality, or the data types are such that it doesn't compress very nicely. Or we go as high as over 20x compression. We have an active customer today. It's a Microsoft internal customer where their raw data is well over 100 terabytes in size. They dropped it into SQL DW. They can't even push it beyond 10. So these guys used to run 120 approaching 200 terabytes, and now they can't even drop it below 10. So that works extremely well if you have things set up nicely. So memory pressure. We need memory to compress, as mentioned earlier, and there's a bunch of fixed overhead that we need to go pay. Number of columns, the types of columns that you have. Integers work better than strings. Short strings and long strings have different impact on compression. If you want more details, we provide the link there on how to calculate the amount of memory you need, and we'll show you the queries that pulls that through also. We also need memory to go build the row groups. And a few things that will affect the memory or how much memory you have available, certainly your slope, your service level objective, DW100 versus DW6000, you're going to have very different amount of memory available to build your row groups. So as you deal with larger data sets or more complex or high cardinality data sets, you want to consider loading data or re-indexing at higher slow levels. Certainly your resource class, those who are familiar with that determines how much memory is available to you also when you run queries, complexity of your load. If you do a C task, create table as select, and that select has a 25 table join, guess what? You're going to burn a lot of memory in just building that join before you even load data. So you're going to run out of memory to build quality row groups. Partitioning we talked about. Degree of parallelism, we don't often see people pay attention to that. FYI, you are able to specify option DOP equals to something or other, and there's a sliding scale on depending on which slow you're running. We pick different levels of DOP. If you find that your data set tends to be more memory hungry, then you may want to consider reducing the DOP, because each node we can run up to 6 DOP, or we can bring it back down to 1. You may want to consider bringing the DOP level low, even if you're running DW6000, just because your data is has the nature that it's high cardinality, or you use a lot of string column types that requires more memory. So trimming will occur, as mentioned earlier, when we don't have sufficient memory. It will occur if the amount of memory required is greater than what's available. And an example here in one of the tables is the amount of memory needed for the different types of columns where you have either just pure integer types, your minimum table overhead, how much memory it's going to need, versus if you start having short strings and long strings. As you can see, the amount of minimum memory required will grow and change quite significantly depending on the column types that you have, the string size that you have, and whether it's long or short strings, just because we have different levels of memory requirements to encode these while we're doing compression. Good example to look at, so from looking out here, let's say if you need, I don't know, one of these guys here requires something like 300 megs of memory. You want to figure out, are you using the right slow, the right DW level, and are you using the right resource class when you're loading this data, when you're doing your C tasks? You want to figure out whether you have sufficient memory. Go look at the query that we talked about. There's the links in the slides. Go look at that, do the calculations, and it will show you how to do that here also. And then you compare that against what's available to you on this end. So if you need at least 300 megs of memory, you probably don't want to run anything less than a medium RC, and you can probably get away with DW600. Maybe you'll need 1,000. Probably safer to go with 1,000 just to ensure that you have sufficient memory. You can always scale back down if you find that, hey, things are running really well and you're not seeing any issues. Test it to see what's the right sweet spot. But this is pretty much as low as you want to go. Any lower, then you're probably going to run into memory pressure, and we'll look at the DMVs that will show you that you've built unhealthy row groups, or worse yet, you got a bunch of Delta stores running around, which means you're not leveraging the power of cluster column store. DOP makes a difference. I mentioned earlier, different DW levels gives you different degree of parallelism. We make decisions internally on what the max DOP is, but you can provide a hint in your query, as mentioned earlier, put an option DOP equals to whatever value that's desirable. In some cases, even at DW6000, you may want to run at DOP 2 or even 1 if you have data that has very, very high cardinality. For instance, some of the customers we work with that deal with credit card fraud type information, some of those columns are just naturally have high cardinality, and we typically have them load data at DOP 2, no more than that, just because we want to get good quality row groups. Dictionary pressure is the other thing that we talked about briefly earlier. Again, if you have high cardinality, we have a max size, the dictionary size of 16 megs in memory, and that can't be changed. That's not something that users can go look at and decide, I'm going to go bump this up and change the value of that. So that's kind of fixed. We're looking at potentially making that better or higher, but for now, if you exceed the size, you will see a trim reason that says dictionary pressure, and that means you have a couple of things that you potentially can do. If you have these strings in a very wide table, are friends with 200-300 columns in a table, you may potentially want to break that up into more than one table. I don't like that solution because breaking it up means subsequent queries, you're going to have to join them, and that may be a very high price to pay, make the loading better, but then everything else below that will be awful because you load it once or you load it incrementally, but then you query it many, many times. So be careful with that recommendation about breaking things up. It works for some people, not for everybody. The other thing that will work for more folks is optimize your types. And what that means is if you're picking varchars and you're picking a default, my standard generation says everything is varchar 4000. It's like, okay, do you really need that? Probably not. Pick only as wide a definition of your data types as you need, and don't go anywhere beyond. Remember, you can always expand online. Shrinking is hard because that typically requires data movement, but expanding is fairly easy. So if you define a varchar 8, for now, and you find, hey, we have new entries coming in from a merger with a different company, this needs to be wider, it needs to be varchar 12, that's a simple online operation to expand. So be selective about it, keep it very narrow. We find that tends to be easier to implement for most people with minimal impact down the pipe. So the one really handy DMV, this was released fairly recently. I think this link here, it's a blog that Shivani wrote. Yeah. So highly encourage you to review that. So this basically gives you really, really good information about the health of your column store. And essentially, you can look into the physical statistics of what it is and where it breaks down to. And I'll show you real quick what some of those things look like that we just talked about. So this view basically takes advantage of this DMV that we just showed you earlier in the slides. Essentially, it just goes ahead and joins with other catalog views, so we don't end up looking at object IDs with a bunch of numbers, and then you have to go convert and figure out what it means. It joins with the catalog views to figure out, okay, what are the actual names of these objects, and make it a little more readable. And the same thing for memory grant piece, the link that we provided earlier. This is where you can go out there and do estimated calculations. This tends to calculate on errors on the higher side. So the chances of you hitting this and the actual requiring more memory is extremely low, probably non-existent. But it does tend to err on the higher side, so you probably will use less than actually expected. So let me just jump right down to queries. So following on with the tables that we looked at in the previous demo, if we look at this non-partition table and the output of that, oops. Let me just slide this a little over to this end. So you look at the number of compressed row groups count to be 9, and the number of actual rows at 25,000. This is clearly not a good place to be, and even though there are no open row groups, these are compressed, it's really on the low end. This is below of what our optimal is, or sorry, what our minimum acceptable is, which is 100,000. And
you meant 1 million. It's below 1 million.
Well, 1 million is ideal. Minimum acceptable is 100,000.
Yes,
so
yes.
Yeah,
it's above the minimum. Yeah.
So let's go figure out why that's the case. Remember, we already removed partitions, so why is it bad? Well, that's because, look at that, we have memory limitations we talked about earlier. So we probably loaded this at a low DWU level and a low slow, your service level objective, and we may have used an incorrect resource class. So instead of using large or medium or extra large RC, we accidentally use small. And that actually happens a lot, because how many of you create your server and your DW as server admin yourself, and then you do all your work using that same account? Come on, we got a bunch of DBAs here to do the same thing. How many of you who do that know that if you are server admin, you're stuck at small RC, and you can run SP add role to large RC or whatever, nothing happens? Didn't know that? Well, that's one of the reasons why you don't get a lot of memory. So you could have been really good. You follow best practices and you say, SP add role add myself to whatever extra large RC, and like, I'm going to go load data. I have a lot of memory now. Guess what? silently does not do it because he assumes that admins are not supposed to be doing these kinds of heavy lifting. Admins tell people to go do stuff. You know, don't you admins have minions that go do these things for you? Apparently that's not the right assumption. So if you do that today, pay attention to that and very quickly check to make sure that you're using the right resource class. You typically need to create a separate user and put that user in the right resource class. Your server admin, you cannot change the resource class assignment for that. And that's one of the reasons why you have memory limitations out here, and you look across the board down there, we're just hitting that every step of the way. And that's one of the reasons why the quality is poor. Now, the estimated memory grant, remember we talked about the view earlier that does the calculation. So what we did here is go look into that view for that specific table, and the estimated minimum is 224. So going back to the slides we saw earlier, you need to go back to and look at, you probably need minimum DW 600, and you probably want to be medium RC or higher. Probably don't need to go beyond medium, but you need at least medium. If you're in small, you will not be able to generate good quality row groups. Now, we created a new table. I'm not going to do that here because, you know, it's like watching paint dry, but we created a new table using a large resource class, and we kept in the same DWU levels. All we needed to do was a larger resource class, and this time, if you look at this table, same view that we created, now you notice we don't have that memory thing anymore. Either we see bulk load or no trim. No trim's good, because we're not going prematurely closing these row groups because we're running out of memory. Bulk load simply means that we've completed that batch process. These are the remainders. These are the leftovers. There's not much you can do about that. So that one's okay. And if we compare the two tables that we worked with, so the first one is the non-partition that had the memory limitation. It has basically over almost 500 of these that were prematurely closed because it ran out of memory, whereas the ones that we used a higher resource class, essentially there is no trimming whatsoever, and it has fewer row groups also. So imagine the amount of I/O that you need to make for each one of these things, how many times you need to go fetch pages from this. Even if you're running SSDs, it's still I/O operations. You still pay the cost for that. These things are not free. So making sure that you have this trimmed down effectively using the right resource classes can have a huge impact on your performance. And the last thing to show you here is the effective space. Now, bear in mind, this is a fairly small table. You know, it's only 100-some million rows. It's not really big. But even at that small level, you notice we already have about a 10% space saving just by using the right resource class. Those of you who are running into hundreds of billions of rows in your table, that could be potentially a huge savings on disk. I have the test table, the fraud transaction database, data warehouse that I work with has a table with over 1 trillion rows. That single table on this size is about 26.5 terabytes, one table. Imagine the kind of savings you're going to get out of that. And this is not unusual. We have a lot of customers into the hundreds of billions of rows, and they're running happily there and running very efficiently. So keep in mind, and these are the scripts that are available. All of the stuff's available online. You can go download and test it yourself. But really, it's really important to pay attention to these different aspects of how you put things together and monitor the quality of that. And Shivani will now walk you through how you can actually load it correctly the first time around so you don't have to deal with this.
Right. Thank you, Joe. So we gave you a lot of information up until this point, a lot of theoretical information, how things work, as well as knowledge from the field for what we have seen in terms of health and what healthy column store means. What we want to do next is give you sort of prescriptive guidance that you can implement in your ETL or ELT jobs so that you walk away with a checklist that you can use to calibrate your ELT implementation and ensure that you are doing things to set yourselves up for success with SQL Data Warehouse. So there's primarily 7 things that I'm going to tell you to keep in mind, okay? And I have a slide on each of these to go into details, but this is your checklist. So number 1, size your batch loads correctly. Okay, we have talked about this in a fair bit of depth, but this is of utmost importance. Partitioning guidance, again, we've talked about it quite a bit, so you need to be careful how you implement partitioning in SQL Data Warehouse. using the correct resource class. So this is very important for making sure you don't run into memory pressure, because the amount of resources that are available to your loading thread in SQL Data Warehouse depend on the resource class that the user is part of, okay? Number 4, if you do run into dictionary pressure, what can you do to your schema? And Joe sort of alluded to it, but I will just show it to you again so that you have it handy as a checklist item. So what can you do to avoid dictionary pressure? Because anytime your dictionaries reach 16 megabytes, your row group is going to get trimmed, even if you gave it enough memory, even if you put it in large RC to get enough, a million rows. Dictionary pressure can preempt everything else. Use updates and deletes judiciously. As we saw, these have a negative impact on your column store quality, but if you do need to do some DML, some transformations, we will briefly touch upon what are some of the things you can do. I will also talk about something called secondary B-tree indexes, also referred to as non-clustered indexes in SQL Server land. So we do have these available in SQL Data Warehouse, and it can be very useful for you to set these up on your column store tables before you start doing your loads, because column store will automatically maintain these, and these can come in very handy for those needle in a haystack queries, okay? Lastly, I'll give you a tip on how to improve your segment elimination. We saw the example where segment elimination was pretty poor because your local bounds for each segment were pretty much your global bounds. So there are some things you can do, and we'll look into that as well. So as we said, the minimum you want to target per batch is 100,000. So what does this mean in terms of number of rows for your batch size? If you have no partitioning going on, this means you need to have at least 6 million rows, which is 60 times 100,000, at least 6 million rows per CTAS or bulk insert. And if you do happen to have 4-way partitioning, you're talking about 24 million rows per CTAS or bulk insert, all right? If you want to increase your bar a little bit and not go for minimum row group quality, but go for optimal row group quality, which is 1 million rows, what you're talking about is 60 million rows per CTAS or bulk insert. And if you have 4-way partitioning going on, it's 240 million rows per CTAS or bulk insert. So I put these numbers just to put it in perspective what sort of batch sizes we are talking about here. So if you have a scenario going on where changes are arriving from your online system and you're staging them in Azure Blob Storage before you do your batch loads every few hours, what does this mean for your batch windows? So let's look at the scenario number 1, where we were targeting 100,000 rows with no partitions per column store, which basically came to 6 million rows required for each batch load. So what does this mean for your batch windows? Let's say your incoming row rate is roughly 500 rows per second, 500 changes per second, right? So this means your batch window should be around 3.5 to 4 hours to collect enough rows to make your column store get loaded in a good way where data goes to compressed row groups, right? If you have an incoming rate of 1,000 rows per second, you're looking at roughly half of that, which is 2 hours. With 2,000 rows, you're looking at a batch window of 1 hour. So this sort of gives you a way to compute how long you should collect your changes for before you start loading your data warehouse column store. I think we've talked about partitioning a fair bit, so I won't go into it anymore, but just bear in mind, over-partitioning will impact your row group quality, leaving very little data for each column store. So a good rule of thumb to keep handy when you're designing your partitioning is to make sure that your targeted data set allows for at least 6 million rows per partition. This will give you the minimum bar, and if you want to do better than that, ideally try and target 60 million rows per partition. And if you cannot ensure this, then it is time to revisit your partitioning scheme. Maybe it is too granular, and as Joe said, don't migrate your daily partitions from SQL Server as-is to SQL DW. It will not serve you well. You want to revisit it and maybe do monthly or yearly partitions. All right? So Joe explained the balance between memory available and memory required. So use that to figure out how much you need, and then select the correct resource class. And some of the other things you can play with, if you cannot just get a high enough resource class on your service level objective for your data warehouses, you can consider scaling your data warehouse for your load windows. And that's one of the benefits we get from the elasticity of SQL Data Warehouse, that you can just scale it for certain windows to cater to different types of workloads. So if you are loading very large tables, very wide tables, and you need large amounts of memory for your loads, you can temporarily scale your data warehouse. Keep load queries simple. If you do need to run transformations, like Joe was mentioning, multi-way joins, sorts in your load queries, please stage it to a heap or a clustered index first, and then CTAS from there to your column store. Because otherwise your compression will have very little memory left by the time the engine is done with the other operators in the load query. And lastly, force serial execution. If you still find that by choosing the right resource class, simplifying your load query, scaling your DWU to as much as your budget permits, you still cannot get sufficient memory, you can use the max stop hint to force serial execution. A word of caution, we did tell you to increase your resource class from small RC, but don't go overboard with this, don't over allocate. Let's not just set everything to large RC or extra large RC. Try and come up with the optimal one. If medium RC is good enough, go for that, because using a larger resource class does impact the concurrency of your system. So if you have 20 concurrent ETL jobs that you want to get going, and you set them all to large RC, essentially they will queue behind each other. So you want to be cautious about dialing it just enough, not too much. So I think Joe already covered how you can work around dictionary pressure. I won't go into this. We don't have a very good solution for this at the time being, and there are some workarounds like separating out the problematic column into a separate table, revisiting your data type choices. NVARCHARs and NCHARs are expensive. They will fill up your dictionaries more quickly, so using more optimal data types instead of those. So updates and deletes. These do have a detrimental effect on your column store. Ideally, you don't want to be doing these, right? So if your workload is such that you do want to run transformations in your SQL Data Warehouse, then we recommend that you first stage your data to a heap or a clustered index, and then load it into your column store, because doing transformations directly is not going to be optimal. But if you do need to do transformations on your column store, please build in alter index reorganize or rebuild into your ETL jobs on a regular basis. Rebuild will basically flush all rows from Delta stores, clean out bitmaps. It is heavyweight, it is offline. Reorganize is lighter weight, and it is an online operation, but it will not flush out your Delta stores completely. So there is limitations. Ideally, you should not require to do either of these if you follow the guidelines. So secondary B-tree indexes. So for the most part, analytic queries just scan large amounts of data. But every now and then we have found that customers have asked us that, I have this predicate where I just need a few thousand rows or a few hundred rows retrieved from these billion rows. And the query takes very long, even with segment elimination working well for me. So we provided support for B-tree indexes on top of your column store. And these are maintained automatically as you load data into your column store. Since they are maintained automatically, there is an overhead, so you do want to just have a handful of these, not hundreds of these, as it will slow down your loads. We did some in-house experiments with TPCH data by creating a B-tree index on order key, and the query to search for a certain order returns in sub-seconds on terabyte of data. We have a real-world usage of B-trees, a very happy customer, Yammer. As most of you might know, Yammer is basically Facebook for the enterprise, so they are using SQL Data Warehouse to track all their user activity. So, all the click streams, logs, user endpoint access, everything is tracked in SQL Data Warehouse as fact events. They use it to basically A/B test every new feature they roll out, They track key metrics for user engagement, growth, acquisition, and stuff like that. So they had this fact events table, which has roughly 300 billion rows. It translates to about 40 terabytes worth of space, uncompressed. And prior to their speaking to us, their query, which would basically, so the support occasionally gets a call from a user who is experiencing a problem. So the first thing support does is they go and see what this user was doing in the last few hours or day or so, right? So they run a query of the form, like I've shown here, select top 1,000 from fact events where user ID equal to blah. So, when they just had the fact events as a column store, this query would sometimes take 10 plus hours or not even return. So they spoke to us and we said, you know what, this sounds like a very good use case for creating a secondary B-tree index / NCI. So they did that, and what they observed is that this query now always returns in under 5 minutes. For some users, it returns in a few seconds because it depends on how many records a given user has. The more records a user has or more active they have been, you will have more records to access from the B tree and go back to the column store. So it always returns in under 5 minutes for them now, sometimes in a few seconds and sometimes a couple of minutes. So it works like a charm. So something to keep in mind for your point queries. All right, so segment elimination. So we looked at the example during the demo in the first part of this session where your bounds were not tight enough to get good segment elimination. Our column store today is not ordered. This is something which we are looking at, but until then, there are things that you as a user of a SQL Data Warehouse can do to improve your segment elimination. So obviously, if your data arrives ordered naturally in some dimension such as time, so if it's time series data, it will be ordered by timestamp, you will get good elimination if you're querying for data within a time range, right? So that will happen naturally. But if it is not arriving ordered naturally, what you can do is first stage it to a clustered index. A clustered index is a B tree, hence it's going to sort the data. And when you do a select star from a clustered index, it is going to come out sorted. So then you can just create table as select from your clustered index into your column store, and you will sort of mimic this ordering of arrival of data, right? Bear in mind, an alter index rebuild today will mess up this ordering that you might have engineered by doing this pattern. So, try to avoid it. And the good thing is, if you follow all the guidelines that we have so far given you, you will never really need to do alter index rebuilds. So you should be good. With that, we come to the end of this part of the session, and I'm going to hand it back to Joe, who will show you what you can do to load data efficiently into your column store.
Thank you. So we've looked at how cluster column store is laid out, what the underlying structure is. We looked at what are the things that will affect your quality of your row groups, and all of that will have direct impact on perf. So how do we make sure that we can follow these guidelines and still be able to load lots and lots of data within the time window that we have? So there are, for better or worse, lots of options, and these aren't the only ones, but these are the common ones that we've seen in our customer space. And there really are a lot of tools that you can use to go push data into SQL DW. However, not all tools are equal. What we've listed here, and you can see the first three being kind of grouped in a little green box there. These are the recommended tools, at least from our perspective, if you want to batch load data really, really fast. And when we talk about fast is in a number of different ways. The first thing is the actual throughput. How many terabytes can you push through per hour? And also, does it scale as you push more DWUs? You set up to a higher slow level, will you get improved performance? So these three are the only ones that actually meet both the criteria. So what it means is, if you can run data loading at X terabytes an hour on DW1000, you move it to DW 2000 or 6000, then you're going to get corresponding reduction. It's not going to be completely linear, but it gets pretty close. So using Polybase and working in one of our customer data warehouses, we were working with them on a proof of concept, we pushed it to about 6 terabytes or so, approaching even 7 terabytes an hour to load. That's a lot of data to push through in an hour. Some data warehouses aren't even 6 terabytes in size. So we push it that hard, pulling from Blob Store. Of course, you need to make sure that data lands in Azure Blob Store first, but once it lands there, and you can do it many different ways, AZ copy, we've had a customer POC where we actually shipped hard drives to the data center just because they had massive amounts of terabytes and they had very little time. They wanted to go push it up there and didn't want to burn the telco bills, so you can ship hard drives to Azure data centers. They will push that into Blob Store for you, and from there, we can push it over 6 terabytes an hour. Now, SSIS and Azure Data Factory, both, at least as of early this year, also use the Polybase infrastructure under the hood. So earlier iterations of ADF, you would not get the same performance, but today, ADF also has the option of using Polybase to load data into SQL DW. There's a little asterisk around SSIS because your vanilla install of SSIS will only have the regular data copy or data movement tasks. You don't have the Azure SQL DW optimized data movement task. So you need to download the SSIS Azure feature pack. It was released earlier Q1 this year. I can't remember the actual month, so I decided to pick June. That's got to be safe. There's no way you can download a version that's June or later that doesn't have this. And once you download and install that, you can now use the task for loading into SQL DW from SSIS. And that's actually really cool, and it will actually use Polybase under the hood. And I'll explain why Polybase works a lot better than the others. So these are really the tools you want to use. The other caveat is, if you can avoid it, really try not to use something like Stream Analytics or Storm, where they constantly push a few rows per second. That's going to cause you all kinds of interesting grief. If you really have to do that, as Shivani mentioned, push that into a staging table. Push it into a heap, clustered index, whatever. Push it in there. The cheapest, fastest way to get in there, once you've accumulated enough, then build your clustered column store indexes. Now, why does that make a difference in Polybase? Let's take 2 slides to walk through this. As we saw at the start of the presentation, SQL DW is an MPP architecture-based SQL data warehouse, and it has the notion of a control node, and both SSIS and even ADF before that, SSIS traditionally would talk to the control node and it would go connect to it. As I mentioned, it has the data movement controls where you would copy data from a source to target, and it would just hit control, push everything through that. So that's really where your bottleneck is. Everything has to run through control node before it lands into the compute and finally to the disk. Now, those of you who are quite clever with SSIS, or you've done data loading in general, figured, hey, I'm just going to run multiple instances of SSIS. I can do that fairly easily. Well, guess what? You can have 200 parallel tasks in SSIS. It won't matter because they will all connect to the control node. So the folks that traditionally, again, this works very well in SMP SQL Server. This is a tried and true pattern, and it works well there. And they can push it really hard on SMP. But in this case, in MPP, it really doesn't do anything for you. In fact, you just saturate the control node, and you eat up connections, you eat up resource, your concurrency slots, and you're not getting any better throughput. So the script to do that is fairly straightforward. I'm not going to go through this. You can go review it at your leisure. But what happens is, this is how we load parallel using Polybase T-SQL. And what the SSIS team did was basically take all of that stuff and work the way Polybase does, which is, instead of going through the control node, it would actually use Polybase under the hood. So when you create a task in SSIS for Azure SQL DW loading, under the hood, it would create the same jobs that you saw in the 2 slides earlier, create all those scripts for you. So you would use the same friendly SSIS interface, but underneath that, it generates the necessary scripts, the stored procedures, and the tables that it needs to create underneath, and it loads directly into the compute nodes from Azure Blob Store and hits the disk. So that way you get the same scale capability that Polybase has. If you scale from 1 node to 10 nodes, it will parallel load all 10 nodes at the same time. It does not have to touch the control node. This is how it gets the performance gains. This is how Polybase works under the hood. And the SSIS team, good friends of ours, we basically work with them to make sure that they can optimize and take advantage of this capability instead of the traditional way which goes through the control node. So in summary, what they really did was, in the past where you had to go through steps 1 through 4 here, and you have to do that manually in T-SQL. And I know there are a lot of DBAs and developers among us in here, and you're like, I eat T-SQL for breakfast, lunch, dinner, sometimes for snacks. I can write these scripts while I'm asleep. Good for you, keep doing that. That works very well. But those of you who are familiar with SSIS, or you have friends in your office, that like SSIS, they're not as tough as those of you here, they want to play with the GUI thing, that's okay. SSIS automates basically steps 3 and 4 to you, so even the task of using AZ copy to move data locally into Azure Blob Store, and it creates stored procedures in SQL DW to perform the data movement operations, push thing in there, and the other extra thing it allows you to do is all of the traditional controls in SSIS for your transformations, all the things that you're familiar with, you can apply those also either during or after you've loaded. So essentially, it's automated all the scripts for you that we kind of went through very quickly in the previous 2 slides. But those of you who've used Polybase for loading, those will be exactly the same kind of scripts. All this thing does is it automates that for you. So makes your life a lot easier, and this is how SSIS was able to go from trickle into a few gigs per minute, or at best a few hundred gigs an hour, down to multiple terabytes per hour, just like what Polybase does. So no big secret there. Essentially, we just shared how we do it, and they implement the exact same thing. So we're getting right to the edge here, so I'm not going to walk you through the scripts out here. Let's make sure we have enough time for the summary and Q&A. So you want to walk us through the key takeaways?
Go ahead.
Okay, so we covered a bunch of stuff out here, and I know we went varying levels of depth and went a little deep on some and we went up in other areas, but what we really want to make sure you take away is column store behavior is very, very different from row store, and it's very different between SQL Server, SMP, and SQL DW, which is MPP. There's a huge impact of those 60 distributions. And keep in mind, today it's 60. That's just a number we picked for a number of different optimization reasons. There's nothing preventing us from bringing it down to 2 or pushing it up to 180. In fact, we have tested these things in the lab, and we can push it as high as we want to. We've gone up to beyond 180 distributions. So these patterns, understanding the impact of when you lay it down on SQL DW MPP architecture is really important, because that way, as and when we enhance the product and go for much larger scales, your principles will still apply, so long as you keep that separate from your SMP principles. The loading methods and efficiency are really, really important. You need to take into account multiple factors from the size down to memories and the tools that you use. So make sure that you understand your data patterns coming in, make sure that you understand the memory requirements, and look at some of the DMVs, some of the views that we've created on top of these DMVs. These are all provided to you as part of the session. Review those things regularly. The thing to also remember is some of these operations, after you've done it, fixing it via rebuilding indexes may not be feasible. We think about data warehouse as a tier 2 workload, it's not business critical and so forth. The reality is a lot of data warehouse systems are now becoming business critical or close to it. People get really mad at you if the data warehouse was down for a few hours because you need to do a bunch of maintenance. 5 years ago, or even as recent as 2 years ago, most people get away with that. We have customers that would start calling us or opening support tickets if it was down for 5 minutes. I work with 2 of these customers, so they actually have my personal cell phone number. Not a very healthy way to spend time. But this is important because we need to make sure they're healthy. So make sure you do it right initially. Avoid these kinds of rebuilds down the line. Partitioning is one strategy that helps you minimize the rebuild effort, and a lot of people very quickly jump onto it. But remember all the stuff that Shivani talked about, partitions can cause you a lot of grief also. So you need to find a balance there. Maintain and monitor. We've given you a number of DMVs and also pointers and links in the deck, so you can look at. Highly encourage you to review that. We've given you some guidance on what to look at. Do monitor and check on that on a regular basis. The ETL patterns, look into your environment, look at the tools that you're using. Both of these things, they come into play. We're working with as many vendors out there as we can, including third-party tool vendors, and we want to help them be as optimal as possible. But as of today, the 3 tools that you saw listed earlier, those will get you the fastest loading performance possible, and those will scale as you increase the DW levels. That's the key thing, right? We talk about, pay compute for the compute that you need, and in this case, it really is. You pay for more compute, you get better performance out of it. And we have many customers that have their loading windows where they will bump the compute up to the DW6000, so they get the maximum throughput, and they will load it. And once the loading window is done, then we'll bring it back down to 2,000 or 3,000 because the daily query activity doesn't require that much. So they literally bump it up every day, up and down when they need to load, bump it up in the evenings, load very quickly, make sure they have enough time to run through the validations and monitoring, make sure things are healthy, bring it back down, and then the next morning the users will come in and they'll have fresh data running at a lower DWU, which lowers their overall operational costs. So that brings us to the end of our session. Do remember to complete the evals. Let us know what you liked, what you didn't like, what else we should do to improve. Tell them if you want us to come back next year, although I think it's still in Orlando. I'm not sure if that's a good thing. But really, give us a feedback. Let us know what's good and what's not working out for you. We'd like to hear that. And if you have questions, we're going to hang around for a little bit longer. If not, thank you very much for coming to our session and for attending at night.